This conference will now be recorded.
For coming along to talk by Nick and myself on the subject of track engineering aspects of the Eastleigh Derailment, which happened on the 28th of January 2020, so just over a year ago, as Tim just said there. And we're going to concentrate on track engineering learning from that, and out of all incidents and disasters, there is learning, and that's what we're focused on in tonight's presentation. I hope you find it interesting. We've got about 25 slides, so we've computed at 1 minute 30 seconds per slide. There'll still be time for questions at the end, so let's stick to that. We couldn't have produced this presentation without a lot of information and input from colleagues in other organisations. So I just want to acknowledge that input from Pandrol, which is 20 years old. So when they originally tested the Balfour Beatty RT60 bearer system, Serco, who have done some tests for us, Building Research Establishment, who've done more tests, Rabe, I've pinched a couple of John Graham's diagrams, and Mark Burstow, who many of you will know, who's the wheel rail interface expert at Network Rail. So I've unashamedly plagiarized some of their stuff. So a quick introduction to the incident first, just to describe what happened. The site of derailment was at Eastleigh Station, and oh, sorry, spare that. The site of the derailment was Eastleigh Station between the switch hills and the crossing of 450 Alpha points. Derailed train was a Freightliner Class 70 loco, which was hauling a mixture of load and empty container wagons. The loco and the first 6 container wagons, which were all loaded, derailed. The train was crossing from the down slow line to the down fast line. Recorded speed of the train was 12 miles per hour. There was absolutely nothing about the derailment which points in the direction of any issues with the train or the wagons, or the way it was being driven as being a contributory cause of derailment. Track construction was Balfour Beatty RT60 design of switches and crossings on concrete bearers. And the cause of derailment was gauge spread under the loco, and that was due to the failure of consecutive housings on the outside of the turnout curve. One of the great benefits, of course, of concrete bearer S&C is its resistance to gauge spread. So this is in many ways an unexpected and calamitous occurrence. That's a track diagram of the Eastleigh Station area where the derailment took place. So London is on the right and Southampton is on the left. 4 lines through Eastleigh, well, 5 lines, I suppose, if you count the loop as well, around the back through Eastleigh Station. And the freight train had pulled into the down slow platform, which is a common move for freight trains at Eastleigh heading towards Southampton. They do crew changeovers in the platform, and then the trains go across 450 Alpha Bravo, crossover and back onto the down fast line for their journey to complete their journey to Southampton. And as I said a minute ago, the gauge spread was actually between the heels of the switches and the crossing in 450 Alpha points, so not in the movable part of the switches. This is a more detailed diagram of the actual location within the S&C where the derailment took place. So the switch tips are over here on the right, and the crossing is over here on the left. And these are the red and orange dots represent the positions where housings failed. The red dots represent housings which failed in fatigue. The yellow dots represent housings which failed through brittle fracture, which we believe happened during the derailment. and the green ones were intact after the derailment. So you can see from that, so there's 9 housings altogether that failed, and that was enough, that enabled the rail to move sideways enough for the train to derail. So that's a photo of all of that. So the switch tips are here. We're looking towards London there. The train was travelling towards the photographer, and these are the housings that failed. So you can see the nature of the failure there, where the housing has snapped below the level of the main casting, and it's the shank itself which is cast into the bearer which has failed. More of that later. So this is a cross section. It's a schematic cross section through this part of a Balfour Beatty RT60 S&C layout. So several interesting features of this design. So firstly, to emphasize that it's Sen 60 rail. Secondly, that it's inclined S&C rather than vertical. And this particular design of S&C is one of 4 designs which were developed on behalf of Railtrack by S&C suppliers to meet the desire to run higher speeds and heavier traffic on parts of our network, primarily West Coast Main Line in the first instance. And the design is that there is a wedge-shaped piece of casting underneath the rail, which gives the inclination and maintains the level of this part of the rail, the same as the level through the movable part of the design, where all of the slide base plates and so forth are in place, roller base plates as well. And the way that happens on the effect of that on the housings is obviously to make the housings higher above the bearer than they would normally be, particularly on the outside of the curve. So on the outside of the curve, that raised housing is some distance. The actual housing itself is some distance above the bearer level, and then below the bearer you have these studs which hold the castings in place on the bearer itself. And there's the usual rail pad there underneath the rail, directly under the rail, and there's another thin pad underneath the wedge. The failures that took place happened below the bearer surface, so they weren't visible to staff who were undertaking visual inspections until the shoulder actually detached from position. So, and that green dotted line there shows the level, the approximate level at where they all failed, so between 30 and 45 millimeters below the surface of the bearer. It's perhaps clearer what's going on in that isometric drawing there. So that's an introduction to what actually happened at the derailment in terms of what was immediately obvious. I'm going to hand over to colleague Nick Carter now, who's going to take you through the inspection and testing programme which followed in the aftermath of the derailment, and from which we have learnt a lot. Nick, over to you, please. And tell me when you want me to move the slides on, and I'll do that. Hello, Nick, can you hear me? Hello?
Nick, are you muted? Can you unmute?
Hello?
Hello, we can hear you now.
Hello. Sorry, connection issues again. Good afternoon, everybody. Thank you for inviting me to this meeting. So as Andy has said, obviously we had the derailment at Eastleigh. One of the things we initially done was recovered 8 housings from the site, and we sent them away to Serco for metallurgical testing. We also set 6 bearers aside from the derailment site with a view to having these tested later on at BRE. And as part of that, we decided on 3 phases of testing, which we will go through later on. If you could go to the next slide, please, Andy. So of our 8 failed housings, 6 of them basically failed in fatigue caused by the bending and the tensile stresses being applied. This led to the fatigue crack initiation on the surface of the shank, followed by the propagation through its thickness, until it got to the point where it suffered an overload and it literally just sheared off, as can be seen in this photo. One of the things that we did notice, or that was picked up on as part of the initial testing, was that the point of the crack starting, shall we say, was always at the same location. You could go to the next slide. Oh, you've done it. Thank you, Andy. So following the chemical derusting, as can be seen in this photo, there's 2 different zones. You've got the fatigue area and then the overload or the brittle failure. Fatigue cracks, as I said, initiated from the fins on the shanks. There was no evidence to suggest that there was any casting defects whatsoever, so we attribute it to a design. Next slide, please, Andy. So the fracture faces that you can see show different housings recovered. As we said, they all initiate from the 12 o'clock position and then towards the rail where it was fitted. So housings 20, 21 and 24 all failed due to fatigue, whereas housing 26 was a brittle failure. Now housing 26 was one of several that failed, as Andy shown on the previous slide. This was the only one we kind of had tested. If you could go to the next slide, please, Andy. So the fracture faces on the 3 housings that failed due to fatigue were heavily corroded. This kind of indicated to us that the 3 that we identified initially were probably broken for several months, possibly even longer, whereas the other 3 housings didn't have the same level of corrosion. So it's probable that they were broken or fractured for weeks, but again, it is possible that it was longer, possibly months. However, these are only best guess judgments, and as it says, we cannot confirm that was a definite issue or a definite cause. Next slide, please, Andy. So moving on to the bearers, we contacted BRE, and following initial phone calls conversations, we agreed on 3 phases of testing. Phase 1 was a visual tactile inspection of the bearers themselves. Phase 2 then consisted of some more destructive testing, so to speak. We actually sectioned the bearer, and phase 3 is planned to take place in the coming weeks, which will be a load testing of a new bearer and an existing old bearer which was undamaged. So interestingly, one of the things that we noticed was the cracking along the top of the bearer. Previously, this was thought to be an indication of a potential issue with the Balfour BT system. However, we have since been led to believe that this is not the case, and we'll allude to that later on. The cracks themselves were no more than 0.4 mil wide between the anchor seats, so it's not significant. Next slide, please, Andy. So as I said previously, we sent the bearers away, and phase 2 was to actually have a bearer sectioned up to see what we were getting and what was actually going on with the structure. So the cracks that were visible on the surface, it transpired that they were relatively shallow, going no more than approximately 50 millimeters deep. One crack did extend past that, but that was put down to potential causing as part of the actual sawing process. Typically, once they got beyond the 40 mil depth, the cracks were less than 0.1 millimeters in length, in width. So, you know, irrespective of what was going on, it wasn't significant. It was also noted that the cracks themselves, while they ran through the cement matrix, they also passed through the aggregate particles, which would indicate that this had happened after the concrete had hardened and not while it was still set in its plastic state. There is a possibility that this was down to dry shrinkage, and they've aligned themselves to like the location of the anchor points, which is something that's not uncommon for the sort of bearer we've got. What we did find was the cracking was not consistent with alkali-silica reaction or something along the lines of a sulfate attack. The distressing strands within the bearers were also of good condition, and there was nothing to suggest that they'd moved or anything of the such. There was no corrosion present either. What we did find was we cut through one of the sections as close to the pandrol anchor as possible, and it exposed the epoxy pocket surrounding the anchor. I think we were pleasantly surprised at what we found. We were expecting there to be cracks going through it or it not to have been seated properly. However, it wasn't. It was a very good relationship. The mating surfaces were really good. You'd not ask for anything better. We did notice there was a crack. Well, there was a crack that extended 120 mil below, which was less than 0.1 millimeters in width. And again, it's difficult to determine. That could have possibly been caused by drilling, but it might not. It was nothing to cause any concern for us at the very least. Next slide, please, Andy. This is just a picture of where we'd had it cut down the side of the anchor, and as you can see, the epoxy itself is very well sealed against the concrete bearer. The crack, it's very difficult to know where they've highlighted it in yellow, but it was, yeah, that's what we could get. Next slide, please, Andy.
I think it's just worth adding at that point, Nick, that the dotted line around the epoxy there is just a dotted line, and there were no, as Nick has said, there were no cracks around that epoxy pocket at all. No,
it was a very good interaction of the two different materials. We couldn't have asked for anything better, to be fair. I think it's fair to say that it was a good sealant. So one of the bearers, the one that you can see, obviously one of the housings had sheared or was missing. So we had that bearer cut through that location. Interestingly, as we've identified, the housing was missing approximately 33 mil below the surface, which seems to be a consistency we're finding with all the sheared bearers, or the sheared housings in the bearer, should I say. The remainder of the anchor was perfectly bonded. There was no issues. We found no pockets or anything like that, and there was no evidence of cracking around the vertical edges of the epoxy either. I think that's identified in the next slide. But as you can see here, it's the bearer's been cast. It's then been cored. The epoxy's been filled, and the casting has been set in place. And again, there's nothing to indicate any issues or any cause for concern in terms of the strength and the rigidity of the componentry. I don't know if there's anything you'd like to add to that, Andy.
No, thanks. Good explanation.
And to be fair, that's kind of where we've got in terms of testing to date. As I said previously, we have got a new bearer and a old bearer that was in the track but undamaged, currently on their way to BRE, and they're going to be undergoing some load testing, which I'm sure Andy will discuss later on.
Good stuff. Thank you very much, Nick. So I'll try and rattle through the rest of the slides as quickly as we can, so there's some decent time for any questions. These photographs and text relate back to 2000 and 2001, where Pandrol carried out product approval testing for the BBRT60 raised housing design. And the photograph on the left is of the first test, which is testing in accordance with the relevant SENS standard. What they did was load cycling between 5 and 117 kilonewtons applied at a rate of 4 hertz for 3 million cycles at an angle of 21 degrees to the vertical, 15 mil below the bottom of the gauge corner radius. So the horizontal component of that load is about 36% of the applied load at 21 degrees. So the horizontal component cycles between 2 and 42 kilonewtons, and the bearer successfully passed that test without any significant damage at all to the components. That was followed up the following year with a modified, with essentially the same style of test, but modified by a rail track specification. And the modification was that the test load was cycling between 5 and 100 kilonewtons, but it was the same 4 hertz for 3 million cycles, but the loads were applied at 40 degrees to the vertical. And that meant that to mimic how that gets its way into the system, they had to chop off the head of the rail and machine the web so that the line of action of the force as applied met the requirements of the specification as shown in the photograph there. Of course, this significantly increased the horizontal component of the load to 64%. So you were getting the maximum cycling load of 64 kilonewtons. So quite a big increase, about a 50% increase in the lateral amount of loading. And again, the assemblies passed with flying colours. In both cases, the only thing that was noted in the Pandrol test reports was that there was some minor cracking of the around the edges of the epoxy pockets, but it was felt to be a cosmetic issue, and there was no other deterioration noted. This is an exciting techie slide from Dr. Mark Burstow, but it is full of absolutely fascinating information. So this is an extract from some vampire wheel rail interface modelling that was undertaken by Mark and his team, and the model is using loads from the leading bogey of the loco through the actual, using the wheel profiles as measured on the loco, using the rail profiles as measured from site, and using the track geometry information as measured from site, critically in terms of curvature, but also other aspects of track geometry. And if you look at the, so the switch toes are located 116 meters into the simulation, which is the scale along the bottom. So the switch toes are here, and the train is going that way from left to right. The first fracture is here at about 128 meters, and the subsequent fractures are in this little zone here. And as it says here, large flange forces were experienced from a point about 4 meters beyond. The modelling shows that about 4 meters beyond the switch toes, you start to get these very high forces. I suspect it's just a function of the model that it rises as steeply as that. Whether that happens in practice, maybe it doesn't, but you can see that the loads are consistently lateral loads of around 100 kilonewtons, and then even higher in that next section there, up to peaks of nearly 140 kilonewtons. This is for the train moving at 10 miles an hour, and those are pretty consistent. This diagram shows how the wheel rail interaction is working. So there are 2 points of contact between the wheel, shown in blue, and the rail, shown in black. So there's a point of contact on the head of the rail and a point of contact on the gauge corner. And the leading wheel set, so that's the first wheel set on the, it's a 3-axle bogie. The leading wheel set has got very high flanging forces on that gauge corner, which are acting as near as damn it horizontally on the rail. Whereas on the trailing wheel set, the flanging forces are much, much lower, and the majority of load is vertical load going into, or nearly vertical load going into the head of the rail. So very, very different behaviours between the leading and trailing wheel sets, but you'll remember from the cyclic load testing done back in 2000-2001, the maximum load that was cycling through laterally was around 64 kilonewtons in the 40-degree test. So only about 2/3 of what's going on here, and maybe half of these peak lateral loads here. Right, a bit about lever arms now. So here we are in the BB RT60 design. The lateral load is going in there. How it finds its way into the fastening system is down here on the edge of the rail foot. Of course, there's a clip here which has to hold this side of the foot down. But in terms of the lateral component, that's where it goes in. So it's going into the housing there. So that's the level it's going in, and this is the level of the fracture in the stud, which is grouted into the concrete, and that's a lever arm of between 85 and 100 millimeters. If you think about where it would be if it wasn't for that elevated housing design and the rail was sitting on a pad at rail level, then that would make as some other designs do, then that makes a significant difference to the level at which the lateral load is acting on the housing and fastening system, and it reduces the lever arm on the stud massively, reduces it down to 45 to 60 millimeters. And then if you think about what it would be like if it was a vertical design, then there's another 5 millimeters again. The load would be even lower, and the lever arm would be reduced to 40 to 55 millimeters. So roughly half of what the lever arm is that was experienced by these castings. So I think we could be pretty sure that the designers had anticipated that there were going to be higher overturning forces from this increased lever arm with the elevated shoulder, because they've made the shoulder wider to resist that force coming on here. The shoulder's been made wider. Whether or not there was any consideration of whether bending moment would find its way into the stud or not is a moot point, and we simply don't know the answer to that. But you can understand that a very small movement here, which could happen for all sorts of reasons, but a very small movement here, fractions of a millimeter, will be enough. Let me go back a couple of slides, sorry. A very small movement here under the action of this lever arm will be enough to develop extremely high stresses in the tensile stresses in the outermost fibers, and this is where the fractures, that's where the fatigue failure was initiated, around these ribs on the fins on the cast-in studs. Right, on to, have I missed out a slide there? No, good. Right, so discussion points to finish. So I've put this one first because, and this is a personal opinion, all of our issues around gauge spread, not all of our issues, lots of our issues around gauge spread are in very, very tight curves. This particular derailment is another example of that. It occurred at the sharpest radius in this particular S&C layout and the radius about 195 meters. So had that been in plain line, it would have required a check rail. It's not in plain line, it's in S&C, it's not protected by a check rail. So all of the curving forces are taken on the outside rail. So if you think back to this, all of the curving force is finding its way into this housing. It's not shared with that one. It's all finding its way into this housing. And when a wheel sits there, the distribution to adjacent housings probably isn't very much. So it could be that that maximum 100 to 140 kilonewton load is finding its way pretty much unshared into one housing. Could well be the case.
Slide speed.
Elevated shoulder design successfully passed its load testing. So just to emphasize, it had been through all of our processes to certify it as appropriate for use. These housings had failed about 15 years after installation, so the track had given good service up until that point. The method of freight working at Eastleigh, we talked about at the start, crew changeovers, so, and then crossing over 450 Alpha Bravo points to get onto the down fast line. So these points have seen continued heavy loading from freight since the day that they were installed in the turnout direction. A lot of this S&C sits with it taking loads on the through route, which wouldn't be an issue, but in the turnout route, these are probably some of the most heavily loaded points like that in the network, certainly on Wessex. Class 70 loco weighs 130 tons, got triple axle bogies. They exert higher lateral curving forces than double axle bogies because they're longer. And as I've said, lateral flanging loads of about 100 kilonewtons with possible peak loadings above that. The elevated shoulder design increased the bending moment. We've discussed that. Was that bending moment considered the design stage as a moot point? Clearly, bending moment was sorry. The impact of the extended lever arm had clearly been anticipated in the design of the housing, but whether the shank was considered is another thing. And they're just to say that they're shaped like that to have better fixity than a smooth design. So I understand there were issues in the early days of cast-in anchors with them coming loose within the concrete. The really gratifying thing about the slides that Nick showed is that those anchors were really soundly fixed into those bearers. They weren't going anywhere, but they've snapped. Okay, last slide. Surface cracking of the bearers doesn't appear to be contributed to the failure mechanism, and that was the opinion of our BRE, and it's our opinion as well. Track geometry recording trains. This is interesting. So the track geometry recording train travels through 450 Bravo alpha points in normal when it records the down slow line, and then heads off towards Fareham. The down fast line is recorded as the down fast line, so there's no track geometry recording through that crossover. And with hindsight, you can say, well, that's the predominant route for freight traffic is through those points. So should they be part of that? Well, that's a moot point, but it wasn't. And it's not practical to record all crossovers around the network. But maybe with crossovers that take such regular heavy traffic as this, that should be a consideration maybe. One insulators on the outside of the curve could be a precursor indicator of lateral movement. And just a little thing about this design as well, which applies to other applications, not just BBRT60, is that the the rail pad has to be in exactly the right position in order to get the insulator in place. So it's quite a tricky task. If the pad has moved, it's quite a tricky task to sort that out and then get it to get the side post insulator back in place. Future work, which we're already out to research colleagues and the market with these 3 things that we want to try and develop. We hope to be successful. It's not guaranteed. So the first thing we're after is a simple, affordable method of detecting dynamic lateral movement of the rail foot. When we thought about this in a bit more detail, initially we started off saying measurement of gauge spread, and that's not really what we're after. What we want to know is that the rail foot is moving sideways. We don't want to know that the head's moving sideways. We want to know that the foot's moving. We want it to be easy installing. We want it to be easily monitored by inspection staff or even remotely, as long as we can afford it. Can't afford it, it's pointless. Ideally, we'd like a handheld NDT method to identify fractured housing shanks. It's not really something that's amenable to ultrasonic testing because the area that we're interested in is buried in the concrete, and if you put a probe onto the top of the housing, there's a dirty grey airspace underneath it where the clip goes. So it's not really amenable to that, but we think there might be other opportunities through things like maybe acoustic or vibration applied to the housing, which might show it. And then the last thing is, which is work in progress now at technical authority, so thanks to colleagues for picking that up, is a revised housing design with a stronger shank for drill and grout housing replacement repairs. So the majority of this S&C is giving excellent service. The vast majority of this design of S&C is giving excellent service. And where we are having 1 or 2 issues with broken studs, we can get them drilled out and replaced. But we do want those replacements to have a stronger shank than the ones that are breaking. So that's the end of our presentation. Thanks very much for listening. And Nick and I are happy to take questions.
All right. Thank you, Andy and Nick, for a fascinating talk, and really coming up with some quite detailed problems to solve. We've got a couple of questions through in the chat. If anybody else has got questions, could I indicate they've got a question in the chat, put it there, or just do that, and I may ask you to unmute and ask your questions. But first one we got from John Hilliard, which I think you've sort of answered in the last slide, but you may want to add to it. It says, were additional inspection requirements rolled out across the network on similar units remaining in service, especially near depots or freight loops?
So there's been a special inspection notice to carry out tactile inspections of all of the S&C that has this design, where there are freight movements taking place over them, and if those tactile inspections raise any concern that there may be a fractured housing, then the fastening is removed and the housings are given a safe thump with a hammer. And there have been, I think, Nick, correct me because I'm going to go wrong here, I think there have, as a result of that nationally, there have been something like 6 locations found where there were some fractured housings. Have I over-egged it?
I think 6 is the number I recall, Andy.
Yeah, which have mainly been in a similar position, which is around this between the crossing and the movable length. There have also been a couple of examples where these raised housings have broken at crossings.
Right, that's interesting. Have you done any analysis of crossovers that actually get such a high loading as you have had at Eastleigh with that type of movement?
So all of the routes have been asked to do a risk assessment on that basis. I don't have any information about what the results of that are.
Okay, Bob Hazel's got a question. Did the slow speed increase the forces on the leading wheel set compared with the trailing wheel set? Would a faster speed have sort of brought the forces closer together?
What a fascinating question. So Mark Burstow did an analysis at 25 miles an hour, and I haven't put that slide in here, and I can't remember top of my head what that shows in terms of the relative distribution of forces between leading and trailing wheel set. It's intuitive, Bob. I think that the faster the train goes, the more equally that flanging load would be shared between leading and trailing wheel set. I think intuitively that makes sense. I do remember from the slide that the peak lateral load was slightly higher at 25 miles an hour than it was at 10, but I can't really say more than that.
Right. Bob's got a second one asking what the gauge was. Did wider gauge 1435 versus the 1432 allow increased lateral forces to allow a greater angle of attack? The ball and claw arrangement allows the gauge to spread more easily due to the lack of additional longitudinal restraint compared with heel blocks. Now,
two-part question, masquerading as one.
Yeah, that's typical Bob, I think. Get his money's worth.
1435. What was the allegation there? That 1435 does what?
Allowed increased lateral forces due to allowing a greater angle of attack. Or you've got an extra 3 mil if the front wheel set is hard against one rail and the trailing one is hard against the low rail.
That's a question for discussion down the pub, and I'm in danger of vastly going beyond what I can reliably answer. 1435 generally you would expect to bring benefits for curving through S&C, and I think it's one of the benefits of the NR60 design. I think that it has that wide gauge designed in. Notionally, it feels like that 3 mil shouldn't make any significant difference to angle of attack, but I'd defer to more expert people than me. What was the second part of the question?
Andy, I only asked the question because I've been doing some work on light rail systems, which have, as you know, some very, very tight radii compared to what we're used to on the mainline railway. And very interestingly, they don't allow gauge widening because it creates more wear.
What sort of radii? What sort of radii are they working at?
Bob, what do you mean? I know light rail can go down to about 25 metre radius curves. It's not down to 20 in some places, from my experience. So we do get very tight radii on those. I think
generally, as a maintainer, as opposed to a designer, I've grown quite fond of sensible gauge widening, but I confess I'm not really sighted on the sort of detail of the loading. And then your second point was around the ball and claw versus heel block, and whether that increases the likelihood of or decreases the fixity of the rail. Again, I don't have an opinion. It's an interesting observation. It sits in does not compute for me. I need to go away and put the cold towel on and think about that.
Right. We've got a question from Jason Grocott. Did the high lateral loading on the outside of the rail, with the high lateral loading on the outside of the rail, was there any sign of rotation and stress on the gauge face clips?
So I can't be definite about that. It is, again, intuitively, it must be the case that those clips on the inside of the rail were taking very high uplift forces. I didn't mention that the testing program, of course, also included some very severe pull-out tests on this design, and it sailed through those pull-out tests without any problems. I don't remember anything about any particular damage or distress to the insulators or clips on the inside. Nick, do you recall anything about that?
I think the interesting thing with it was, Andy, the housings when we got them, there was no clips available, and what was on site had been damaged beyond, I think, recognition from the wheel sets as they've gone over. So it's a difficult one to kind of quantify, to be fair, because we haven't got the evidence from Eastleigh to say yes or no.
Are you aware of any reports of broken clips on the inside? I haven't heard of any.
I've not seen anything. There was, looking at some of the previous inspection records, there was nothing to indicate. And from memory from my time at Eastleigh, it didn't ever stand out. It was the other end that was always the concern, to be fair.
They're pretty meaty clips, these, aren't they? They're not the old design of handheld clip. They're the modern beefy ones with high tow load, 12.5 ton tow load, so they're pretty meaty clips.
Seems though the questions seem to get longer as the questioner gets older. Next one is from John Dolan. He says, towards the end of BR, there was a device called the Gauge, developed by a chap called John Gay in the ACE's Birmingham. It fitted underneath the rail across the forefoot and gave measure of how the rail moved under traffic. It was designed for use in sidings where there was no track recording, and it required someone to put in place, and it didn't transmit data. So I think that one of the manufacturers took it up. Is there something that could be done, something like this, with more sophisticated technology?
Absolutely. My own personal hope is that it's something which wouldn't need to worry about the low rail, that it could just be sitting underneath the high rail to sort of save having to go across the forefoot. But with that proviso, we're open to any suggestions from our research colleagues that are affordable and simple to fit, and as John says, they're brought up to date so to do monitoring rather than just taking a single measure. So, for example, you'd want to be able to look at a week's worth of data and say, right, under freight trains, I can see that it's moving out 3 mil. Under passenger trains, I can see it's moving 1 mil. So it's that sort of a thing that we're after. But absolutely, the principle that John's explained there, it's the sort of thing that we're after.
Yeah. Oh, good.
Sorry, Tim, just following up on that. It actually worked the way a max and min thermometer works, in that it told you what the biggest gauge you got at foot level, but it didn't tell you what had happened other than the biggest one. So it was a fairly straightforward mechanical device that simply slid along and then stayed at its biggest measurement. So that's basically how it worked. fairly simple, fairly easy to use, but as Andy says, you know, you've got to keep checking it.
Yeah, with modern sort of measuring devices, you might be able to do something even with something as simple as a strain gauge or something in places with some sort of.
That's the sort of thing. I'm really hoping there'd be something small that you could like glue to a bearer or something like that, and just leave it there and point your thing at it and download it from time to time.
Well, yeah, I think even more, it transmits straight back to space if something's exceeded. You might be able to sort of, as you say, glue a plate to that which has got a strain gauge on it, and if the strain gauge goes up above a certain level, it does a report. Right, Jim.
These
Jim
things
Wheeler.
have moved on fantastically, and we've maybe been a bit slow to exploit some of that, I think.
Yeah. All you need is that and a mobile phone, which is not a great deal of money in reality. Jim Wheeler has come up with one. A quick calculation of cyclic loading suggests that this site might have done the 3 million cycles in the past 15 years. So it might be right at the limit of the tests done by Pandrel. Also,
that's a good observation, and it will. My view, I've only done fag packet calcs and which are completely unreliable, but my view, it's probably gone a little bit over the 3 million. It will have done at least the 3 million. Yeah.
He also said it's interesting to look at this event in context of the customer. And he says all Freightliner crews change crews here. Why? Because the available pass forces a crew change here due to the multiple looping forces. I'm sorry, because of available pass forcing crew changes here due to multiple looping forces excessive transit times impacting on crew max shift times. Keep the traffic rolling, I think. Also, I think that there's a 15 mile an hour marked on the crossover, so speed limit. But a C switch should be suitable for 25. A faster speed may have reduced the lateral loading, which is going back to Bob Hazel's remarks earlier.
Yeah, no, I suppose you might question whether a longer switch would lessen the loading as well, because the radius would be not so tight, but then you've got to fit it in amongst all the other operational requirements for S&C at Eastleigh. So but they're all sound observations
Right, and Brian Counter asks, was there any indication of unusual damage or distress that could have been seen by track inspection visually?
Well, with hindsight, possibly. We've had a small number of failed housings in a switch at Basingstoke, which have been repaired, and that showed that the housings that were removed showed that the rail had actually worn its way into the side of the housing, which also indicates that the insulator must have either been that the insulator must have completely worn away under the lateral loading. So you deduce from that, as I said in one of the comments at the end there around the discussion, that distressed insulators could be a visual precursor. The other thing that we've included in the post-derailment inspection, which we issued a SIN for, was to look for signs of cracking around the epoxy pocket. So the way these bearers are made is they drill a hole after it's been cast, and then put put the housing into the hole and grout it up, and when the housing's pushed into that hole, obviously the grout is displaced by the shank, and the housing itself then typically sits on a thin skim of grout around the edges. And what you can see, which again is a possible precursor, is sometimes you see cracking in around the edge of that, around the edges of that epoxy. So it's not affecting the pocket itself, as the cross sections have shown, but that may be a precursor sign as well. And that's one of the things that when people do the tactile inspections, we've said if you see this, then you should remove the fastening and give it a tap with a hammer.
Yeah. Well, Bob Hazel got a bit of information here from MTR in Hong Kong. They have developed a very simple lateral movement gauge. It is glued to the bearer, not mobile, but cheap enough to be a fixed bit of RCM.
Who makes it? How much does it cost? Where can I get them?
I think Bob will you can be in touch with Bob afterwards on that one over a pint somewhere.
Yes, please. Yes.
Maybe virtual pint, I don't know. And just for your last comment,
is it called the Hazel Gauge?
Yeah. No comment from Bob there. Is he still here? Oh, yes, he is. I can see him there. Right. And John Wesley, he said, would an inspecting hammer blow emit a sound warning of a housing fracture like a wheel tapper?
Yeah, I suspect it would. We spend a lot of time telling our staff not to hit castings with hammers, and so I think we need to carry on bearing that in mind. But absolutely, we think that the sound would be different, and that's part of our thinking that there may be an NDT technique that involves putting some vibration or sound into the housing rather than trying to do it through ultrasonic means.
Yeah, I thought ultrasonics was putting sound into a housing, but anyway.
Oh, blast! Yes, you're right. You know what I mean?
I know what you mean. Yeah.
Because it would have a different harmonic response as opposed to how it reflects signals backwards and forwards. As John is suggesting, we think it would sound different. Yeah.
Yeah, I think for a lot of these things, for getting the right sound warning back, you need to have a hammer of the right weight to do it with.
I'm thinking it's just something like an agitated tuning fork that you sit on the outside of it, and if it sings a perfect C, you know everything's right. But if it sings a B flat, you know something's wrong.
Yeah. I hope you got perfect pitch then. Yeah. Right. That's the end of the questions. And a fascinating range of questions, actually getting quite technical.
Can I just thank the audience for a brilliant set of questions, and I feel quite mentally exercised.
Yes, there's another one just coming from Jim Wheeler. Sorry, Jim. Thanks, Andy. We need to mark switches for their design speed. The old Southern region way of marking speeds down because all drivers exceeded the speeds. No speedometers in those days is out of date. But today all trains have speedometers and drivers are dead scared of exceeding the marked speed. I think it's obvious that the bearer system failed at the weakest point, but most turnouts of similar designs will not get the same level of loading. Maybe we set a life of 25 years before replacement of turnouts of this design. So, and maybe you might identify other ones where you bring it down to 15 or 10 years if you've got an identified heavy movement on a regular basis.
I think Jim's on the right lines there. So what we're hoping for So rather than just relying on the empirical evidence that we've got from this derailment, which is that the housings have lasted 15 years, and I think we could actually and should regularise Jim's fag packet calculation there to try and identify the number of cycles with a bit more certainty. But the barrier testing, which the further phase of barrier testing that Nick talked about earlier, is intended to establish how many cycles of loading, so it's cyclic loading, but it won't go up and down. It will just be constantly high cyclic loading. How many cycles cause distress in the bearer and possibly cause the housing to fail. So that's the intent of the final phase of testing, to try and put some numbers against that. Our view at the moment is that it's only a small part of the total population that is at risk, and we'll need to manage that in the sorts of ways that Jim has suggested. But the rest of it, that's taking mainly through route traffic, should last, 50, 60 years, because it's flipping robust stuff.
Yeah. John Wesley's just asked, he missed the first 15 minutes of the talks. So he's asking when was the layout installed, and that was about 15 years before it failed, wasn't it?
Yes.
Yeah.
It was late. The late
2002, 2004 it was installed.
Thanks, Nick.
Yeah, 2004, 15, 16 years then, yeah. Okay, right, that seems to be the end of the questions. No one seems to be putting anything else in the chat. So if I can call upon Ken Newell to propose a vote of thanks.
Well, Nick and Andy and Nick, thank you ever so much for an amazing presentation this evening. We're usually watching sort of forensic analysis on the TV, but there was certainly an amazing forensic examination that you've been through over the last year. And it just demonstrates, doesn't it, that how the importance of the learning in the industry, and especially in the permanent way institution, is such a key aspect. And I think it's certainly to be encouraged that this sort of presentation is brought forward, because all this learning is most probably going on at very regular intervals around the industry, but it is actually then disseminating it to much wider. We've had over about 60 people on the meeting tonight. We'd have certainly been a bit crowded in the upper room at Waterloo. so that's certainly a great bonus, actually. Even though the beer's not quite so good here at my rather cold office, but anyway, thank you very much indeed. I'm sure it's been appreciated by all those people who attended, and I hope that the lessons will be rolled out, and that learning that you've brought to the industry. Thank you very much. Let's show now a round of applause.
If you unmute yourself, people can hear you.
Can I just add one thing before you finish, Tim?
Yep.
Yeah, I just want to say, I don't want to interfere your meeting. So a great thank you and a great meeting. But there's no thing as a free beer. You see this wonderful thing here I'm waving about. I hope you like the new journal. I think an article on this subject would be fabulous. So can I just set you that little challenge, Andy? It's lovely to see you, and it would be really, to spread that around the great things. A journal article would be fabulous. So if that's not too much trouble for you and me, that would be brilliant. So that's my request. And the other thing is, any comments on the new format of the journal, I would love anybody to give me anything or send it back to the PWI. But what a great meeting. Well done, the sections, for organising it. Well done.
Thank you. Yeah, we'll put